Welcome everyone to this webinar, and thank you for joining us to listen to information about Eluent pH and how we can explore this as a selectivity tool. So today I'm going to really break it down into two sections. So the first section will be looking at selectivity and why we need to consider selectivity as our probably first parameter when we're looking at method development. And then we're going to look further into actual pH and the use of pH in our method development, how we can look at different workflows with pH, and some of the considerations that we should look at when we're developing methods related to pH. So the analytes, the types of solvents and buffers we use, and the types of columns that we consider. So combining selectivity and pH to give us a real platform for method development. So in terms of what we think about when we want to develop it, most of us want to pull peaks apart. That's the main aim of our chromatographic separation, pulling peaks apart. And we term that as resolution. Some of us are lucky, we have one peak of interest, but generally we have more than one peak and we want to separate them, we want to resolve those peaks. And chromatographically, this is what it looks like. So we want to have the first peak finish before the second peak starts. And the resolution equation that your chromatographic data system will implement is shown on the left of this slide. So it's based on the peak widths and the retention times of those peaks. So we want to make sure that we see some baseline, ideally, between the first and the second peak here. So a resolution with a value of 1.5, that means we've got baseline separation of those two analytes. Ideally, when we're developing our methods, we want to aim for 1.7 or 2. That would be better than starting with a resolution of 1.5. Sometimes it's not possible, but the more separation, the more resolution you have for those two analytes, potentially the more robustness you have in that method in case parameters change. So this is what we're looking for, is good resolution between our analytes. And when we think of this in a more sort of theoretical way, the resolution is made up of 3 parts. One of them is the retention of our analyte. So we need to have an interaction of our analyte with the column under the given mobile phase conditions. If we don't have any retention, the analyte comes out far too early in the chromatogram, and it's very hard for us to get any sort of separation, so resolution from other analytes in that mixture. We need an efficient system, so we need to ensure we have long columns, small particles to give us sharp, narrow peaks. And we also need selectivity. So selectivity is determined by many factors, which we will explore, one of them being pH. And selectivity, as you can see from this great graph, is really the most powerful of those parameters. So we need retention. You can see that indicated by the green graph. We need efficiency, which is a steeper line, but the most powerful part of this equation and the most powerful tool to you as a chromatographer is alpha, which represents selectivity. So the red line here in the graph. So when we think about selectivity, there are many, many parameters that affect selectivity. Some are only for isocratic separations. Those are shown on the left-hand side of this slide. So the column stationary phase, whether I choose a C18 or a phenol column. the organic modifier, so whether I have acetonitrile in my mobile phase or methanol, and the pH. And those are the three most powerful things we have to play with when we do our method development. They are also the three most important parameters when we look at consistent chromatography. So getting a robust method for QC, QA, we need to make sure that we are getting consistent chromatography from our column, we are making up the mobile phase correctly every time, and the pH is consistent. And I'll show you some very interesting differences you can see between very small changes or small modifications to pH. Now, gradients, you need to also consider the K star, which is shown in this equation, which takes into consideration our gradient time, our flow rate, our gradient range, and our column dimensions. So all of these factors influence that alpha term, that selectivity term. We're only going to touch on some of them today, really with a focus on pH, because that is a very powerful parameter to modify selectivity, to modify alpha when you have ionizable analytes. So if you are lucky enough to work with neutral analytes, pH isn't going to have a big impact on your chromatographic separation. But most of us aren't that lucky. We have acids and bases in there, and therefore pH is really something to consider, whether that's making sure it's consistent for your QC or exploiting it for your method development. So we're going to have a look at some of these parameters. So when you look at method development, the simplest approach is to take your favorite column and run your standard scouting gradient with one temperature, one pH, one type of organic modifier, and one actual gradient time. And this is the starting point for most of us. We'll look at probably a C18 in the first case, probably low pH, and then change one parameter at a time potentially to develop our method until we see a separation of all of the important analytes in that mixture. The easiest thing to change is our gradient slope. So we'll change the time of the gradient. And then the next easy thing is the temperature. So these we don't have to make up new buffers. We don't have to modify anything other than within the system, plug in another gradient profile or temperature profile. More powerful is the organic modifier. So changing between acetonitrile and methanol is probably the most common approach. So that can give us more data. If we have multiple columns, maybe a column switching unit available, then we could try different chemistry columns. Or if we were getting coevolution of a lot of peaks on some of the earlier methods, just completely change the column chemistry. And then finally, a lot of us will look at pH. So whether that's changing to 2 different pHs or potentially 3 pHs, this will give you even more information about your sample. And if your sample is an unknown mixture, doing all of these experiments can actually really give you lots more information about what is in that complex mixture. There are other approaches, but each of these is a sensible approach in terms of those parameters affect alpha, they affect selectivity. So they are sensible choices for your method development. We are going to focus on this final box, so where we look at multiple pHs, because that's what the talk is on today. And really some of those real take-home messages about things to look out for when you're changing pH. What is it affecting? What do I need to ensure I'm doing with this strategy? And there are many benefits. I've listed some here. The biggest one is that you change alpha. You change selectivity when you change pH. And if you choose a system that goes to a wide pH, so the buffer is appropriate and the column is appropriate, that wide pH, then you can really see very large differences in selectivity, in peak spacing, and therefore the potential for you to actually separate out all of your analytes of interest. We have multiple buffers that we can try, so you're not restricted by the buffers on offer, and a lot of them are mass spec friendly, so depending on the actual method of detection you've got, you're not limited by the buffer availability. It's something you need to consider, of course. We don't want to be running phosphate buffers in mass spec unless we really have to, you know, divert the flow, for example, as an alternative. But if you know your final method needs to be MS friendly, you can build that into the actual method development process. Finally, and something that I actually have only a couple of slides on, is if you are trying to purify your sample. So if you want to isolate that peak, working at a different pH can give you a different loadability. So we'll touch on that. It's not the easiest of parameters to consider, and that's why it's not the first box on our method development workflow, because it doesn't always have a linear effect on your chromatography. We see many of these method development softwares have parameters to model temperature and gradient. The pH effect sometimes is not as linear. You also have to make up buffers, and that takes time. We need to be consistent, and therefore maybe it's easier sometimes as an analyst not to try 3 or 4 different pHs, because I then don't have to make up 3 or 4 different buffers. And finally, not every column is suitable for an extended pH. So potentially, if you're using your standard column, you might need to go to a different brand of column, a different type of column, to actually be able to run at a high pH, for example. So what do you need to think about when you start your method development with pH as your favorite alpha changing parameter? Are you going to run a screening system? Do you have the ability to column switch, for example? When you're running your method development, are you always going to have pH switching capabilities? What am I trying to achieve at the end of the day? Do I want a final method with a certain runtime and a certain resolution between my critical peak pair? So all of these parameters need to be determined at the start. Do I want to purify my compound at the end? If it's a base, then maybe I want to run that at high pH to achieve a better loadability. Do I know anything about my analyte? In some cases, we will be looking at an API and its related substances. So yes, we have quite a lot of information about the analytes. We know some are acids, some are bases. In other cases, we've got an unknown sample from our chemist and we just need to see what's there. Or metabolomics, we're looking to find that needle in the haystack. So we don't know the parameters, we don't know the properties of every single analyte in the sample. And also the stability of our compounds. If I go to high pH, am I actually going to be degrading my analyte? So all of these things need to be considered. I've mentioned a couple of times, what column am I using? Is my favorite column from the drawer capable of running at pH 10? It might work for a few injections, but if it wasn't designed for that pH, then potentially the lifetime is going to be severely decreased. So making sure I look at those specification sheets for the columns to check I've got the right column for the application. And finally, where do you start? I mean, most methods we would start at low pH. So if I know the analytes of interest, I know I've got a big section of basic compounds that I really need better attention for, well, then I want to work at high pH. But does my column work at high pH, and are those analytes stable? So again, things to think about before you even start exploring pH. When we go back to basic chemistry theory and we look at titration curves, there are obvious reasons why it's better to look at low pH for acids and high pH for bases. And this is clearly demonstrated in this titration curve. Along the x-axis, you can see the mobile phase pH, and along the y-axis, the retention time of this basic compound. So you can see it's got a pKa value of 9.3. This would not be a good pH to work at. This would not be the best pH for you to choose for your method development, because very small changes in that pH mean very significant changes in your retention time if you look at that slope. If you work at least 1 pH unit away from the pKa of your basic compound in this instance, then you've got a 90% ionized or 90% unionized base. What that means is you still have 10% of the other form. In reality, you know, it's an equilibrium, but if you think about it from basic terms, if I've got 90% one compound and 10% another compound, theoretically I should have 2 peaks. In reality, what happens is you just get a broad peak. You get a poorly defined peak. It doesn't look great. And the closer to that pKa you work, the worse that peak shape will be. And the more significant the changes will be if in retention time, if anything fluctuates with the mobile phase composition. So a better place to work would be 2 pH units away from your pKa of your analyte. That's when you're going to have a more stable, more reproducible retention time. So for high pH, it makes sense. We get more retention at higher pH for basic compounds, and we get poor retention at low pH for basic compounds. The opposite's obviously true for our acids. So you see the titration curve goes in the opposite direction. We get good retention when our acids are run at low pH. This is because they're in their unionized form. They're more hydrophobic. And when we're working with C18 type reverse phase columns, that's when you're going to get the best hydrophobic interaction when you have an unionized compound. So low pH is good for acids, high pH is good for bases. And therefore, if you have a mixture of acids and bases in your sample, it makes it hard to choose a pH. But it also means that if you use pH as a method development parameter, you've got a big chance of changing selectivity when you try and explore that method development space. So for example, here we have a mixture of 3 analytes with 3 different properties. Our red is our acid, our blue is our base, and the green is a neutral compound. If we just take different pHs, you can see the chromatograms popping up on the right of the slide. So at low pH, we have good retention of our acid. So that's the last eluting peak on the chromatogram. Our neutral is coming out in the middle, and our base is poorly retained, so it comes out early. If you move to intermediate pH, you can see that the elution order now changes. So our acid is poorly retained and comes out early. Our basic compound comes out next, and our neutral comes out at the end. Then when you move to high pH, you get great retention of your basic compound. See, it elutes last. Our neutral all the way through here is pretty much eluting in the same retention time to a degree. And then our acid is poorly retained and eluting very early. So big changes in selectivity, in peak order, when you change the pH based on your analyte properties. So it's a very useful parameter to explore. When we think about what buffers to choose, we need to make sure we are actually using a buffer. So as I mentioned, the here you can see this analyte. Obviously, we know the properties of this analyte, and under these given conditions, we've got an analyte retention at 20 minutes. Now, very small changes, so 0.1 pH unit change, can cause a significant change in the retention time. So if I'm not running my system with a buffer and something slightly changes in the mobile phase composition, that pH changes, I'm not buffering it, then I can get significant changes in retention time just because it's not a buffered system, I'm not controlling the pH, and I'm too close to this analyte pKa. So you can see here a shift of 2.5 minutes with a 0.1 pH unit change. If someone else has made up the mobile phase and it's got a 0.2 pH unit change here, again, I've got a significant change in the retention time of that analyte. My peaks are moving around. And if I have different analytes in my sample with different properties, obviously they're going to move at a different rate based on their titration curves. So it's really important to use a buffer to make sure you have a consistent pH in the mobile phase, unless you're working with neutral compounds. But as I said, most of us don't have that luxury. 20% change there in the actual analyte retention time. So for an isocratic run, if you have 0.2 pH units different. And just as a nice example that I was provided with, you can see here the top chromatogram has a pH of 2.9. The bottom chromatogram has a pH of 3. So the mobile phase is only that 0.1 pH unit different. And my peaks 3 and 4, which separated nicely in the top chromatogram with a resolution above baseline, so 1.7. Now, if I move to pH 3, they both coelute. So peaks 3 and 4 have lost all of that resolution. They're coeluting with only that slight change in the mobile phase pH. So it's really worthwhile setting up good working practices, SOPs, to ensure that the pH is made up consistently every time. Now you could say, oh, maybe I'm working too close to the pKa. If pH 2.9 is the only place that you can get separation, you just have to make sure you are consistently making that mobile phase up, or do more method development to make sure you've moved away from that steep part of the titration curve. So making up buffers, it is really follow your SOP, but make sure that that is interpretable in only one way. So consistency is a key thing when you're making up mobile phase. Determine the pH, so decide what pH you're going to work with, and then choose the right buffer dependent on its buffering capacity and what detection technique you're going to use. Ideally, we'd say make up buffers from first principles, so calculate the amount of acid base that you need in a salt form, get it to the required molarity, and make up a stock of that buffer. If you have a stronger stock than you actually need in the final mobile phase, then it potentially has a longer shelf life. And if you have definitely a quaternary system, then you can just have aqueous in another line to dilute that. We'd recommend checking the pH with a pH meter in an aliquot rather than putting the pH meter straight into your freshly made up mobile phase. That will help with the cleanliness of the mobile phase. And just a couple of things, don't change, don't try and adjust the pH once you've mixed everything together. You're not going to get accurate readings then. And also don't add the water to the organic fraction, because you might get the buffer precipitating out, so you don't want that crashing out. It's just kind of good housekeeping. When running gradients, it's important to make sure that you are only running a solvent gradient, so a modifier gradient, not actually a pH gradient across the run, because you can see how significant an impact pH has if you also then have a pH gradient. So I have a different concentration in my B line versus my A line, then small changes in the system, if I want to transfer that method to another instrument that has a different proportioning capability, for example, that's not going to give you consistent chromatography. So if you can make sure that you have the same pH in both lines, that you don't have a pH gradient across the gradient time, then that's going to give you more reproducible chromatography, especially if you have to do any tech transfers or are running on multiple instruments. Unless, I mean, there are some methods out there that require a pH gradient. There's a lot of work in hydrophobic interaction at the moment in that area where you have a pH gradient across the run, but that's a designed pH gradient. Make sure that if you only want an acetonitrile gradient, that's what you've got. You don't also have an ionic strength gradient across the run. When you choose your buffer, I mean, there's different types of buffers you can use for your aqueous component. A lot of the time, we use things like formic acid, TFA. Just make sure that if you are looking at pH control, you're using the correct type of buffer. And again, weigh out the salt, adjust with acid and base, make sure that everything is consistent when you are making up mobile phasers. And there's a list here of recommended buffers for HPLC and UHPLC, covering really the whole pH range. So you shouldn't be limited in which buffer you use. For method development, sometimes you can do a mixture of buffers so that you do span the whole pH range, or you can have different buffers in different lines for pH switching, for example. And we have a nice guide which helps you to choose buffers, which you can download from vwr.com. So you need to consider your column. I've said that. The reason you need to consider your column is because most columns are based on silica. And silica is a fantastic medium that we can bond to, we can modify. It's got great mechanical stability. But at low pH, we have issues with ligand cleavage. So you can get the actual C18 hydrolyzed from the surface and exposes silanols. And at high pH, the silica can actually dissolve. So if you are using a standard silica, maybe one of these older generation type A silicas, you really have a much more limited pH range to work with. So check the care and use of the column that you're currently using. If you want to work at a wider pH range, then there are different types of column that are capable of running at those pHs. So really with these older generation silicas, you don't want to work outside of the 2.5 to 7.5 pH. These new type B silicas, some of the modified silicas, that really expands the pH range. And I think I've mentioned most of this. There are other types of columns that you could consider as well. So silica-based generally gives you a very high performance, very good peak shape for your analytes. So high efficiency, lots of high plate count. But if you really need to go to a wider pH range outside of any of these silica-based or modified silica-based columns, then you can look at polymer-based or hybrid type materials that are designed for pH 12, pH 14, for example. So when we start to think about method development, we go back to this selectivity chart. And we're going to actually look at a number of these parameters, but with a focus on pH. And I'm going to show you some examples of different method development options you can go for. So there are a number based on a fully porous material that we have, and then there are some additional ones based on this solid core format of column. So I'm going to not cover all of these different method development approaches, but cover some of the key ones to get you really thinking, what have I got in the drawer? What can I buy? What columns are suitable for low, medium, high pH, for example? And where am I going to get the biggest wins in terms of separating out my analytes? What platform do I need to set up? And you'll see throughout these examples, we're using Uwe Neuer and the team's way of describing selectivity. And it's based on this equation, which you may have heard me talk about before. And what you do is you run a set of probes, a set of analytes under a given set of conditions on one column. And note the retention time. You do exactly the same with exactly the same set of probes, set of analytes on a second column, maybe from a different vendor. In this case, we've got C18 from vendor 1 versus C18 from vendor 2. And then you plot the retention times. If the selectivity is the same, so you have the same types of interactions on the first column under those given parameters with the second column under those given parameters, then what you'll see is a straight line in this plot. Because they have the same interaction, you get the same retention times. The more similar they are, the lower this selectivity value comes out. So 1 means they're the same column. The higher this value, the more different the columns are, or the parameters are, and therefore the wider the difference in selectivity. For us as method development teams, then that means that's a good choice for another parameter to look at to move my peaks around. It's a good way to change the selectivity, change the elution order, change the retention times. So when you are just using C18 versus C18, they have the same type of interaction, so you get very similar retention times. You can see the fitting value within the graph is similar, and therefore I get a low selectivity value. Here you can see one column, a C18 across the x-axis versus the different type of column chemistry, in this case a C18 with a pentafluorophenol group. And you can see that there is some scatter on the graph. So they don't give the same retention time for all of these analytes. Some of them, yes, they are on that straight line, but some of the others are more scattered, and therefore the selectivity is described as 11 in this case. So I'm running both columns under the same conditions at low pH in this instance, and I've got a selectivity value of 11. So that tells me that the retention time for many of my analytes on one column is not going to be the same as they are on the second column. If I've got neutral compounds, potentially it could be the same. If I've got aromatic compounds, because there's a pentafluorophenol group on this column, I could be getting some big differences in selectivity, differences in retention time for those types of analytes. And what we've done is we've compared a lot of our columns using this as the basis. So same set of probes under the same conditions to compare column versus column, but then you can also bring in other parameters that affect selectivity, for example, the pH or the organic modifier. And then you can see how changing multiple parameters or different types of parameters affect the selectivity. So what should we choose to have the most impact on moving our peaks around in our method development? And here you can see 102 analytes run on 3 different types of column with 2 different organic modifiers, but only 1 pH, in this case low pH. So you can see here the selectivity values that you get for 3 columns. And you can see they're different from each other. They are giving you decent changes in retention. And this is with methanol organic modifier. You can also look at acetonitrile. You'll see here the values are actually lower than in methanol. And this is mostly because of the pi-pi interactions. They're not as strong in that type of solvent as they are compared to methanol. You can still use them, you still get differences, but the differences are more noticeable when you use methanol as your solvent of choice. You can then start to draw in lines between these. So actually the biggest selectivity value we've seen here is just by changing the organic modifier on our C18 column. And you can add in more lines to see higher and higher selectivity values. So the highest is actually between a C18 and a C18 PFP when you change the organic solvent. So you can start to see how these build up and give you an idea of differences you're going to get when you change different parameters. All these columns have different mechanisms of interaction, and that's why they're giving you different retention times. So this is a low pH screen because these are silica-based columns. Above pH 8, you're not going to get the best lifetime from these silica-based phases. Within the portfolio, we do have an extended pH phase, and that's in this case a C18, so it's got that hydrophobic bonding, but it's also got some extra encapsulated bonding technology which enables high pH use without dissolving the silica. So I've still got the fantastic high performance, high efficiency of a C18 column, a silica-based C18 column, but now I can run this at pH 11 without actually destroying the column. And what we can start to do then is replace that C18 with a super C18. So remember, that's the one with the extended pH range. And I can not just exploit low pH, now I can go to high pH as well. And you can see here some of the values are different, even at low pH. When you start to look at low versus high pH, you get some significantly high selectivity values. So you can see here, selectivity of 88. If I have one column, 2 pHs, 2 organic modifiers. What that looks like in a scatter plot is a significant amount of scatter. So changing pH gives you a much wider method development space. And this is why it's interesting when we're looking at ways to develop methods, because we do get such high selectivity values. So here, for example, we're using that super C18 column at low versus high pH, and you can see the scatter is significant. It's all over the graph. And you can see things are grouped together based on the analyte properties. So the bases are at the bottom, the phenols tend to be more at the top. Those neutral analytes still run along the straight line in the center because changing pH isn't affecting their retention. But it's a very powerful way of seeing how different these two parameters are. Low pH, high pH on a C18 column capable of running at those under those conditions. And what that looks like chromatographically is very different. So you can see here an example where we have the basic compounds in most cases being better retained at high pH. So they're the ones with the arrows moving to the right. Peak 6, this one actually breaks down into a free acid when you go to high pH. So what I was talking about earlier with the actual stability of our analytes, we've changed the nature of our analyte. So it's something you need to consider when you're developing these methods. Because it's broken to a free acid, now I've got poor retention because I'm running at pH 10.7. So significant changes in selectivity, and retention, in peak shape. You can see that the bases actually are a lot sharper in especially peak 8, for example, when you run at high pH. It's a powerful way to change your chromatography. If you can't go up to that high pH, you don't have that column in your portfolio, then you can just try 2 different pHs, but maybe think about the column chemistry. So in this case, we're going to look at polar analytes, and we're still going to explore 2 pHs. But in this instance, we're not going to stick with the standard C18. We've chosen a column that's got a embedded amide group. So this is what you'd call a polar embedded column. And this has more selectivity for polar analytes. Gives you more opportunity for hydrogen bonding. It's fully wettable, so you can run it with 100% aqueous if you need to. And what you can see with this phase, so this is a C18 amide versus a C18, is a selectivity of 20 when you're running 74 probes down here at low pH. So you've got different mechanisms of interaction. The analytes are moving in different ways, so you've got some scatter on the graph. And you can use this as another method development approach to compare low pH, in this case, 2 different column chemistries, 2 different organic modifiers. Quite a big difference in selectivity when you see that value of 30 in the middle. You're definitely going to get a different elution order for your analytes. Different selectivity, more opportunity to be separating them out. And again, if you want to then go to a higher pH, these columns are most stable below pH 8. So here we've chosen pH 3 as our low pH, and then pH 7 as a more intermediate pH. Gives you a big space to work with, especially when you start comparing the values you get with the 2 different pHs across the 2 different columns and those 2 different organic modifiers. So here I'm up to 42 as one of my selectivity values, and going the other way up to 48. So that's comparing the C18 amide with the C18 across 2 pHs in acetonitrile. And this is a nice platform then, a mass spec friendly platform in this case, because we're using ammonium acetate and ammonium formate to look at those more polar analytes without having to go to more extreme pHs. So it's not the 85 or 83 selectivity value we saw before, but especially for those acids, the bases, you're seeing big shifts in retention time, big shifts in selectivity. So really low and high pH or intermediate pH, dependent on your analyte properties, are really worth exploring. If you are doing any preparative work, so you want to isolate those peaks at the end, as I mentioned, for basic analytes, working at elevated pH is really going to be beneficial. Now I can show that nicely in this example with amitriptyline. So when you start going to higher and higher injection volumes of concentrations of amitriptyline, like running at low pH, you really start to overload the column. And this is seen here with the peak width increases as you have an increased concentration of amitriptyline. You can see you get the ski slope on the back of the peak. It overloads quite quickly at low pH. When you go to high pH, you don't have the same issue, so you can load more material onto the column without actually overloading the column. And sometimes you'll see one peak in your chromatogram that looks a bit odd, it looks a bit triangular. It might be because you're getting this overloading effect, and moving to a different pH can actually be beneficial for that specific analyte. If you see every peak in the chromatogram looking a bit odd, then it's more likely to do with the system. But if it's one peak, it's more likely to be that analyte specific. So at high pH, basic analytes tend to have loading profiles more similar to neutral compounds. So it's worth exploring that high pH. The final set of examples I want to show here are just based on a fuse core kind of technology. Here we've got 2 chemistries, 2 organic modifiers, and 2 pHs again. And we're very lucky with these phases because they can both go to a wider pH range. So here we've got ultra core phases, they're called, and they can go from pH 1.5 up to pH 11. That's within their recommended pH limits. So here we can compare those 2 different chemistries with different selectivity because of different mechanisms of interaction, with 2 organic modifiers, our favourites, acetonitrile and methanol, and 2 pHs, so pH 3 and pH 10.7. And you can see here some of the values that you're getting when you're comparing that low versus high pH on those 2 different chemistry columns. And what it looks like chromatographically is significant. So here you can see the scatter plots, the selectivity descriptor, comparing, actually in this case it's just the phenyl hexyl, but at low pH versus high pH. And we've got a selectivity of 83, so our peaks are all over the place, in a controlled manner, of course. But compared to pH 3, we are getting significant changes in elution order, retention time, etc. when we go to high pH. And in this case, again, it's 10.7. This is our favourite type of high pH application. You can see co-elution of those peaks 1 and 4, 9 and 6, and 11 and 8 on our low pH screen are nicely separated. Those critical pairs have been pulled apart when we go to pH 10.7. And here you're comparing the C18 versus the phenyl hexyl at low pH with the same organic modifier. You still get very big differences in selectivity. So choosing 2 very different columns and then looking at the solvents, so the organic modifiers, and the pH you're running at can really give you a significant method development space. And it is dependent on your analytes. Here's a nice example comparing the selectivity on a C18 versus a phenyl hexyl for vitamins, and related to the fact they've got all these aromatic groups, they've got potential for pi-pi interactions. It gives you big changes in selectivity. And this is at low pH, I believe. Yeah, pH 2.7. So when we look at those options, we've got a very big potential difference in selectivity. We've got a good space to work in. And the fact we can go to a wide pH range gives us very high selectivity numbers to look at. And the scatter within the plot. So this is C18 versus phenyl hexyl at low versus high pH with acetonitrile and methanol. And that space gives you the highest number that we've seen in the whole presentation, at 85 for our selectivity descriptor. Significant changes in our elution order, retention, and potentially then what data we're actually getting from our samples if we've got unknown samples. So really, in summary, we have looked at different factors that affect selectivity, the pH being really the most significant of those. You have to think about how you make up pH, how it's going to affect your analytes, and also that you are doing everything consistently, because that's really key to getting robust, reproducible methods. You have to choose the right types of column depending on your application. So look at peak shape, efficiency, what pH is going to work best for you. Some of those combinations of different buffers can help in the early method development stages to make sure that you have got a wide range of pH to explore. And what I probably should have mentioned is that pH guide that we have electronically has good ideas about how to mix which types of buffer to cover the whole pH range.